Bristol Community College, Mathematics with Dan Avedikian, Math 131, Elements of College Mathematics, Section 3.1, Problem 13. This is Section 3.1, Problem 13. It says, graph the feasible region for the system of linear inequalities and determine if it is bounded or unbounded. And now we have four linear inequalities. The first one is 2x plus y is less than or equal to 8. The second linear inequality is x plus y is less than or equal to 6. The third linear inequality is x is greater than or equal to 0. And the fourth inequality is y is greater than or equal to 0. So this is the most at one time that we've done so far. Again, I'm going to just deal with one at a time. Don't try and do them all at once. So I'm just going to focus on the 2x plus y is less than or equal to 8 and just ignore the rest of them for now. So 2x plus y is less than or equal to 8. I'm going to start by pretending it's 2x plus y equals 8 and find 2 points that make that equation true. This is step one of a four-step process. So I'm going to make a little graph, a little chart, I should say, next to that linear inequality with an x column and a y column. And first I'm going to put in a value of 0 for x, and pretending that it's 2x plus y equals 8, I would see that y has to be 8. If I put in a 0 for x, 2 times x becomes 2 times 0, and I'm just left with y equals 8. So now I'll get a second point by letting y equal 0, which would give me the equation 2x equals 8. Again, I'm pretending it's an equation, not an inequality. To solve for x, x would have to be 4. 2 times 4 would make 8 equals 8. So now I have the 2 points that I need for step 1. So step 2, I'm going to plot them on a graph. So over 0 up 8 for the first one is over 0 up 8 is right there. So over 0 up 8, I put it on the graph. The other point, 4, 0, x is 4, y is 0, means starting from the origin I go over 4 up 0. So I plot a point over 4 up 0. Now step 3, I'm going to connect those with a straight line. I'm going to use a solid line because my inequality has an or equal to in it. So I'm going to use my ruler. I'm going to put it right on the 2 points that I graphed from the previous step. Connect them. And now I have to decide which side of the line needs to be shaded, down below or up above. So for the final step, which is step 4, choose a test point that's not on the line. Use 0, 0 if you can. 0, 0 is not on the line, so I can use it. So if I put in 0 for x, 0 for y, the x and y coordinates of my test point, the result I get would be 0 is less than 8. Now that's true. 0 is definitely less than 8. So that means that my test point is in the shaded region. My test point is beneath the line, so the beneath the line area is the shaded region, and the other would be the blank region. So everything underneath the line I have on my graph right now is shaded. So that takes care of the first of 4 inequalities. Now the next one is x plus y is less than or equal to 6. I'm going to use a different color to put that on the graph just to make it a little bit more clear. I'm going to do the same 4-step process. I'm going to ignore everything else and just focus on x plus y is less than or equal to 6. And I'm going to pretend initially that it's x plus y equals 6. I'm going to forget the less than. And find 2 points with x and y coordinates that make that equation true. So first, if I let x equal 0, I just have y equals 6 if x is 0. And then to get another point, I'll let y equal 0. And when I do, I'm pretending it's an equation, I have x equals 6. That's very easy to solve, like that. So the 2 points I have for step 1 on my second linear inequality is 0, 6, and 6, 0. So let me plot those on a graph. So step 2 of my 4-step process, 0, 6 means over 0 up 6. Starting from the origin, I go over 0 up 6, and I mark that point on my graph. The other point, 6, 0, means starting from the origin, I go over 6 up 0, and I put that point on my graph, again in red. And now the next step, step 3 of my 4-step process, says connect the 2 points that I just graphed. Again, I'm going to use a solid line because my inequality symbol has the or equal to in it. So I'm going to connect these. I use a solid line. Now I have to determine whether I shade above the red line or below the red line. So to do that, I'm going to choose a test point that's not on the line. I always say use 0, 0 if you can. 0, 0 is down here in the corner. It's not on the line. So I'll use a test point that has an x coordinate of 0 and a y coordinate of 0. When I put those values into my linear inequality, x is 0, y is 0, I have the result 0 is less than 6, which is certainly true. So my test point is the underneath side. The result I get is true. So the underneath side is the shaded side. So I shade underneath the red line. And now, x is greater than or equal to 0 is my next linear inequality. And we see this one quite a bit. That means I want only the points in my feasible region with positive x coordinates. So really everything to the right of the y-axis. So it's going to fill in here. And the last one, y is greater than or equal to 0. I want points in my feasible region that have positive y coordinates. So only those points above the x-axis. Those are the ones that have positive y coordinates. So now, the area that satisfies all of my linear inequalities simultaneously is the area that I'm shading more heavily now. Is that point of intersection between the two linear inequalities and below down to the origin. I have not shaded those other two triangles on the graph. That does not satisfy everything. So let me use both colors, the red and the blue, to indicate the feasible region. So it's the area that's in red and in blue simultaneously on my graph. And now the last part of that question, the feasible region that we've graphed, is that a bounded feasible region or an unbounded feasible region? Well, since it's entirely contained, a finite amount of area, and it does not go on forever like some of the others, this is a bounded feasible region.